My name's Tony Morris. I work for an organisation called NICTA, National ICT of Australia. My job, it's one of the best jobs in the world. It is to teach functional programming. So I'm paid by my government to do this. It's great. So I've been up and down the east coast of Australia. We're mostly kind of all sorted out there. So now I'm over here. And what I'd like to do today is I'd like to talk to you about some challenges that occur when teaching functional programming, and that comes about with such words as Comonads and Monads and so on. And today I want to talk to you about the motivation for those. So if you've ever Googled any of these terms, you probably came across an answer like this, which probably confused you and bedazzled you even more, and you're motivated to understand it better, and you're just sort of in a cloud now. So today, I just want to talk mostly about the practical motivations for these things. I don't want to talk about the details of those, although I will outside later if you'd like. And I want to talk about the reasoning that leads to the discovery of these things. So just to get some concrete things down, this is not about a specific programming language. I'm wearing a Haskell t-shirt. It doesn't matter. The things that I'm going to tell you are not specific to any programming language. There's no emphasis on any other type of programming. It's got nothing to do with functional programming, despite what Google will tell you, or dysfunctional programming, which is, I guess, what everyone else is doing. And then there's all these other things that, these are just words that I hear and I don't know what they mean. And I assume no one does. So I'm just going to sort of establish what I mean by a principled thing. You probably remember the old modus ponens. We have a premise, we have an inference, and we conclude the conclusion. That's all I mean. So I'm hoping, does everyone in here know how to read Java-y sort of C# syntax? Is there anyone who doesn't? Excellent. Because what I'm going to do is I'm going to use that syntax to demonstrate some points to you, okay? And the point here is, this is some Java code here. The point of this Java code is to establish an interface, an abstract interface. And it says, well, if you're given two A's, return one of a less than, equal to, or a greater than value, okay? And there's a reason we write interfaces. That reason is because we can produce data structures that satisfy that, like integers and so on. And then we can derive operations from that. So some other structures, such as a list of elements, such that the elements can be compared for order, is another kind of thing that can be compared. I'm just simply establishing why we have interfaces. From that, we have operations. So list sort will work on all things that have compare. These are pretty basic things. At this point, I hope I've not bamboozled anybody. It's pretty straightforward. We also might define some requirements on all instances of this interface, and that is that if you compare x and y, you get less than. Well, when you compare y and x, you'll get greater than. That's just one of the rules of all instances of that interface. And we'll call these laws. So some people often come up to me and they say, what are the monad laws? You know, have I broken the law? Am I going to get arrested? And I say, well, no, the law, this is all the law is. Instances must satisfy these things. So just to cover off here, we have a principled interface, that is the compare interface. We have some law-abiding instances, integers and strings and so on, and we have operations such as sort and maximum and all that kind of stuff. So that's why we do that. So when it comes to principled reasoning, what we try to do is we try to come up with the interface such that we maximize the instances and derived operations as best we can. Okay? And often these trade off. So if we strengthen the constraints, there are fewer things that have instances, but we can get more operations off that. So a good example of that is you can compare for order. If you can compare for order, then you can compare for equality, but not the other way around. So I'm just going to, this is just a syntax thing, okay? I don't like talking about syntax, but here I go. So this bit of Java code here that you can see, that we've just seen, there's the equivalent in Haskell. Hopefully that's just straightforward. The reason I want to do that is because I have to move into Haskell to demonstrate to you some further concepts. Okay, so is that all? Is anyone cannot read that? Does that make sense? It's just an interface, some Haskell code, a bit of syntax changing. Excellent. So, and I've actually just invented a new programming language as well. So this is Java, except its type system's a little bit better. Okay, and you'll see here that we have an interface mappable on a T. But the thing about T is T takes another thing. Okay, so we have a function from A to B. It takes a T over A and it returns a T over B. Okay, so these ones here where you've got a T and then a T over that thing, that's not going to happen in Java, probably in my lifetime. sadly. Another one of my opinions. So I think we just have to come to terms with that. Mappable, here it is in Haskell. That is just regular Haskell. Okay, so all I'm trying to do here is establish an interface. And I've had to skew the type system to do that. So we might have some laws about mappables. Okay. Now, that's Java 8 syntax. Okay, so that is, if I have a value x and I map a function that takes an argument and returns that same argument, that's the same as just x. So this is one of the laws on mappables. And then this one here, well, it's a little bit more complicated. Let's not try and spell it out. But these are two laws, the identity and the composition law of things that are mappable, in the same way that we just saw laws earlier. So here are some examples of things that map. A list, so given a function from A to B, and a list of A, return a list of B. That is, for every A in that list, convert it into a B with that function. You will find that that satisfies the identity and composition law. And then here, using what's called the reader mappable, given a function from A to B, and then an argument to A, return that same argument to B. So these things are mappable too. And again, identity and composition laws are satisfied. From there, we have derived operations. So again, this is Haskell. That is, given a value, we can just map an argument that we ignore. So don't try and get too concerned with that. It's just simply, it's a derived operation from mappables. So there's a name for mappables, and that's functor. Okay, so there's one bit of vocabulary, all done. Auckland's finished on this one, right? So we've seen the interface for a functor, which is mappable. We have seen the laws, the identity and composition laws, and we have seen instances, that is lists and readers, and we've seen some operations. It's exactly the same principle that you would do, how we did compare earlier. It's exactly the same reason we have mappables. All right, I'd like to pause here. Does everyone understand what I just said? Really? Ask some questions if you don't, please. Okay, I'm now going to assume that everyone understood what I just said. Because we're now going to move into the dark territory of this one. Okay, so you'll notice this is very similar again to the earlier example, and that is it's an interface. I've had to invent a new type system again. That is because I've got T's over things. So a monad is a thing that takes a T of A and returns a T of A for T, for the monad T. And it also takes a value, x to T of x, so it lifts it up into that T environment. There's the Haskell, that's actual Haskell. That's what monad means. It's this interface. So, monad interface has laws. There are 3 of them. They're called the associativity and right and left identity laws. And it's strictly stronger. In the same way that comparing is strictly stronger than testing for equality, monad is strictly stronger than functors, or all monads are functors. This gives some implications. So, of the things that are functors, some strict subset are monads. And for those that are, we can derive stronger operations. So here's some examples of monads, okay? So list is a monad. So if you ever hear the term list is a monad, what we're really meaning to say is that there is an implementation of that monad interface such that T equals list. I can substitute list in there, and I'll be able to satisfy that interface. That's what that means. And same with all these other ones that you may come across. And some operations. So, given a list of T of A, return a T of list of A for the monad T. So for all those monads, I can substitute that in for T. And this operation just immediately comes about. Okay, so it's the same motivation, it's just an interface. It's just an interface. We have many instances, as we've seen, and there are many more useful operations. This is why, this is the motivation. So I'm kind of skipping over some details about what is sequence and so on, but if you'll just believe me for now that these are just useful operations. So I want to talk about, some bullcrap, okay, because there's a lot of it out there. You'll have heard that monads are for controlling side effects. This is not true. I hope I've demonstrated that. Side effecting or effects are one kind of monad. It's one value for T. But monads are in no other way related to side effects. So imagine I'm a fruit grocer and I need to reverse a list of bananas. Do my bananas have anything to do with reverse? And the answer is no. It's the same relationship. Just because I can reverse a list of bananas doesn't mean the bananas are related to my reverse function. Just because effects are a type of monad doesn't mean that they're in any way related. That's just not true. I don't know what else to say. It's not true. It's everywhere, though. Everyone will say it. Something about I/O. Everyone's heard of this, right? Monads, I/O. But the I/O people, the people in Haskell, they couldn't do I/O. So what we did is we gave them monads. No, monads are just useful, so we damn well used them. That's what happened. So something about some specific programming language. Haskell guys, they go and use monads. No, me over in my Python land, we don't use monads. Bullcrap. So something related to a specific monad instance. This monad or that monad has everything to do with monads. No, it's just an instance. And this one came about because a friend sent me a link to a talk just recently where this came up, and it blows my mind. This is like layers of crap. So, you know, you just peel one layer off and there's more bullshit sitting there. So there's just too much. I could go on, but I'm trying to equip you with the ability to recognize this nonsense because it's out there, and I'm hoping you're all aware that it's just an interface. There are instances, there are derived operations, and they're useful. And I encourage you all to go and check that out. So we've covered that, right? That's pretty much it. That's what a monad is. That's why we use it for. There's a thing called a comonad. Now, the prefix co means the categorical dual op. This is fancy words, okay? I'll tell you what that means, at least in this context. It takes a T of A and returns a T of TA. Okay, this is the opposite of join. Remember, join went the other way around. And it takes a T of X to an X. If you remember the early one, it went from X to T of X. So again, it's just the other way around. So a comonad is just the dual of monad. And there's the real Haskell, because that's really Haskell. The other one's not really Java, as I've said. So, just like monad, comonad is yet another interface with laws, again, 3 of them. It has instances and it has operations that come about from that. It's just like all monads are functors, all comonads are also functors. So it's another kind of stricter requirement on things that have map. So all things that have map may or may not have duplicate and extract. All things that do have duplicate and extract definitely have map. Okay, so we can call this however we like. Some people call it inheritance and so on, but it's just a relationship between these interfaces. And for Mark out there, he wants to know what an applicative functor is. I'll tell you, right? It's it's anything that satisfies this interface. And this interface, again, it has, I think it's 4 laws on the applicative, and it's simply an applicative T such that it takes a T of a function from A to B and a T of A return a T of B. So when I say these things, right, I know what happens in your head, right? You go, when would I ever use that? And what was all that gobbledy stuff you just said? All I'm trying to do here is establish the motivation for that. So why would I do that? Well, that's another story, and please ask me about that later. It's just damn well useful, that's why. So that's an applicative. It's just another interface. 4 laws, many instances, many operations come about. So the thing about applicative functors is they are strictly stronger than functors. That's why they're called applicative functors. And they are strictly weaker than a monad. So all monads are applicative, and all applicatives are functors. Again, you want to call that inheritance, whatever you want to call it. That's what it is. So usually some people are kind of like smoking on the top of their head by now. I'm hoping that's not the case. I'm hoping I've held you a little bit, at least to understand the motivation of what it is I'm talking about. So, all these words they're just names for common interfaces. And because they're so common, we have a vocabulary to talk about them. And you will come across this vocabulary, and it may be intimidating, or you may not feel invited to use that vocabulary yourself. But that's just because it's become so terse, because it's so ubiquitous. There's no other reason for it, okay? So I just want to reassure you of that. So please come along and use them, learn them, use them. We use them for the same reason we use the compare interface, okay? We wrote the compare interface because we had many instances and many derived operations that came about, and this is damn useful. Who wants to go and write their sort function that runs on every possible thing? I don't think you do either. So, this is the next question I often get, and this is quite a tough question. I'll give it a crack though. Why aren't they used everywhere? If they're as useful as I just said they are, why aren't they everywhere? Well, I'll try and help you do some pattern matching, okay? So I'm hoping to give you some code. This code, I'm hoping, appears to you to be something you would probably come across yesterday, okay? Maybe you came across something like this. It's not any particular language. It's just another language I invented. So what this language does is it takes, it goes through every element in a list, and if it's null, it nulls out the whole return value. Otherwise, it collects every element in a new list. And here's another example. And what this does is it takes a list, and for every element in that list, it applies to an argument and produces a new list. These structures have a common interface. Okay, so this is a list of a potentially null value returning a potentially null list of values. So that was the first example. This one here is a list of an argument to an A returning an argument to a list of A. And this has a structure. And the structure looks like this. It's a list of something of A to M of list of A. And it has a name. It's called sequence. So if you ever come across this word sequence, it's talking about an operation with that structure. That's what it is. I'll give you another example. So we're going through a list, and for every element, we're running a predicate on it. That predicate may return true, false, or null. All right, so if it's null, we null out the return value. Otherwise, we check whether or not it's true, and if the predicate's true, we retain the element in the list. Then we return that list. Similarly, we go through that list, and we apply to that element the predicate, and also to another value, t in this case. Return the list. Again, common structure. Given an A to a potentially null Boolean, and a list of A, return a potentially null list of A's that are retained. It has this structure, A to M of Boolean, to list of A, to M of list of A. And this is called filter. This is just a name, it's just a term that we use commonly. So, it gets a little bit more complicated here. And we're saying, find the first element matching a predicate in a list such that it's potentially returning null. So, we go through the list and we apply the predicate, we check whether it's null or it's true or so on, and depending on that we return either null or a new list. We do similar for an argument, we apply to it an element and an argument, and again, a similar structure. So, the reason I'm showing you all these is because you may come across code where someone takes that loop that you just wrote and go, sequence. No, where they actually just type sequence, and then they're finished, and they walk out and you go, what just happened? Well, it shares a common structure. Someone just came along, spotted that structure, and then walked away. So the answer to the question, why don't we see them everywhere, is because not all people are familiar with recognizing this structure, and my job is to help you all do that. So I really like this example, right? I think it's a clearer example. It's quite simple, and that is, given a list of lists, go through that list and create a new list by flattening it. So we append on that list, okay? So a list of lists to a new list. Or we might have a potentially null value of a potentially null value, and then we return a potentially null value. We flatten that. So if that value is null, return null. Otherwise, get the value out, the not null value out, which also itself might be potentially null. We've all written code like this, I'm pretty sure. So given a function and a value, apply that function twice to that value. So apply to t and then apply to t again. And there's a common structure here. List of A to list of A. A potentially null of potentially null A to potentially null A, where A is just anything. Argument, an argument to an A, given that function, return an argument to A. That was the third example. And this is M of A to M of A. And this is often called join or flatten, this operation. So these operations come about from the monad primitives that I showed you earlier. I can go and write all of these from there. All monads have these. Some type systems just say no. The reason you won't write the monad interface in Java is because you just bloody well can't. As I said, I had to modify the type system in order to demonstrate it using that syntax. Unfortunately, there are lots of languages for which this is not true. You just can't do it, so you won't see them. So the kind of type system feature that I introduced into my hypothetical Java 88, or whatever version it's going to be, it's called higher kind of polymorphism. Okay, so again, just another fancy term. Some type systems are just humanly intractable. Okay, it is not possible to write correct programs in these programming languages. That's why we don't see anything like abstraction in them. So what happens is you bang out 10 lines of code, you spend the next 10 years trying to make it work, No one's ever interested in abstraction. You'll never see monads. Well, when I say never, I do actually know some people who have tried. They are far braver than I am. Actually, I've tried it in Python and I just gave up. But I have colleagues who have tried it in Ruby and JavaScript, and they asked me for help and I just put my earphones in. So good luck to you. Like I said, the reason so more seriously, we don't see them because these type systems don't allow us to get up to any level of abstraction, because it's just, you know, the smartest person in the world just can't get anywhere with it. So, yeah, it's zero very quickly. My guess is around 15 lines of code. You'd time. So what happens is we enter into this loop, and so the tools, whatever it is we're using, whether it's Java or Python or whatever, they limit your ability to express abstractions. And then what happens is it feeds back and says, well, so the programmer develops the different patterns for solving the limitations within that system. So what I'd like to tell you about is a bit of a story. It's not a true story. Well, it kind of is a story, that's true. But I've changed names, especially the name of the project. So if we imagine for a minute that there's a programming language, just make it up, and it didn't allow the program to generalize on list element types. So if we did want to sort a list of bananas, it would be sort a list of bananas. If we wanted to sort on oranges, we'd have to sort on oranges. We'd have to go and, you know, copy and paste. What if you wanted to reverse, a list of oranges? Yep, you'd have to copy and paste that previous code. Has anyone ever worked in projects like this? I have. Management comes down and says, you must do this. No. So what would happen, I predict, and I hope you will all agree with me, is that soon enough there would be a list reverse project on some open source somewhere where all the list reversers in the world go and put all their different list reverse functions. Okay, and so you'll download this enterprise jar file called list reverse, and it allows you to go and do all the kinds of reversing that it is you might want to do. And if you have a new kind of reverse, you would submit a patch. This exists. So you came along and you said, why don't we come up with a programming environment, a type system or a tool, that allows us to just generalize on all possible list element types. You said that, and you received this response. This is my life. We're just doing just fine. How dare you come along and suggest that we throw away all of our hard work and just turn it into a programming language feature or so on. I think you would probably form some opinions in your head, at least. So I think this exists, and I think it exists because there's unfamiliarity. So I think there are people who are just not familiar with the ability to generalize in that way, in the same way that the list reverse project is not familiar. So I would like it to be the case that everyone was familiar, so we didn't even have to have that discussion. It is my mission to change this, okay, in all of you. I want to make it the case that we all exploit these abstractions to understand them and utilize them. That's me. Thank you. So I do have a bit of extra time. I would really like some questions if you have any. Sure.
You made some quite damning observations about use of dynamic languages. In fact, I don't know whether you specifically intended to be about dynamic languages, but the inability to express these higher level abstractions in languages such as Python. On the other hand, I've been reading about some of the combinator stuff that Reginald Braithwaite has written about, where he gives examples in Ruby, and was trying to figure out how to translate those into a strong type language, and actually couldn't figure out how to do it. The fact that the dynamic dispatch actually seemed to be really important to expressing those abstractions, the typeless calculus. Do you have any comment on that?
I can comment to a certain extent because I haven't read it. I do know that he is doing that though. So I think there's there's a really pessimistic answer that I could say, and that is simply, it's true that he can't figure that out, and he should, right? So that is to say, my expectation is that yes, there will be some difficulty in trying to answer that, but also I'm pretty certain that there is going to be a way to do that without the type system. Within a type. You know, people often come to me and they say, look at this benefit that I've got by turning off the type system. And I go, well, actually, that's not a benefit. Just watch me go and do this. And the goal is not to show off. It's to simply say, here's a new way of thinking. And my prediction is that's the case. So I can't comment any further because I haven't seen it, obviously. But cool. Any more questions? Does everyone in New Zealand now know what a monad is? All right? Sure.
Could you talk about possibly the reasons why, I mean, like, Lisp systematic macros, and I've seen in a few places people trying to do monads and stuff, and
Yes.
System go, well, with the macro system, we don't need this position because we can just expand the macro over, so you get similar capabilities, but different capabilities. Is there any reason for one or the other?
It's true with macros, like who wants to go and write sequence over and over for all the different monads? The Lisp people would say to me. I go, well, not me, I'm on your team here. Well, then macros. And I go, no, I'm not on your team anymore, right? So I would say that this is like so close to being good. It's so close. But the answer to the question is I want to be able to write my specific function that's related to me if I'm a fruit grocer, whatever it is. I want to write that function to run on any monad. And I want it to be a first-class value. So I just want sequence. I just want to be able to pick it up and throw it around and do the things that I want. And Lisp is somewhat limited in that ability. Only ever so slightly. It's so close. Like it'd be a subtle distinction argument. So we'd probably be there for hours. And yes. But still, doing better. Like Lisp is doing damn well fine for the 1950s. That's just, like seriously. Come on, man. Good work. Let's try harder. So, so green shirt. That can do which one? Like express these? Oh, absolutely, yes. Did I not mention these? Haskell. Scala. Agda. That's it. Pretty sure. There will be a couple of others. I just can't think of them right now. But yeah, not many, as you know. I'll give you some examples that can't. Like any .NET language can't do it. I've never seen one. C Amiga, F#, NML, none of them can do it. Scala, Idris actually, and I think Freg can do it. So yeah, not many. You could write them down in a little piece of paper and carry it with you, and you'd have every single one. Sure. Yep.
Some languages that can express these complex type systems. What about languages that can express the laws? So for example, you can't express the monad laws in Haskell.
Yes, that's an excellent question. Okay, so to sort of to continue the analogy, if we had this, say, the compare interface, and there were some laws, right? If you compare x and y and you get less than, you swap them around, you get greater than. How do I encode this in the type system? How do I make it so that all instances satisfy this law, and if they don't, then they don't compile? And yes, you're right, Haskell doesn't do this, okay? So you could be a malicious programmer, and these exist, by the way. They come along and they go and write this thing, and they call it a monad, and it doesn't satisfy the laws. It compiles, but it doesn't satisfy the laws. So what happens is you get people who go, is a monad, but doesn't satisfy the laws, which is to say it's not a monad. And I really wish we would just say that instead. But yes, there are type systems in which you can express the monad laws, such as Coke and Agda. They do this. Some people do it as a pet project on a weekend because it's just damn fun. And I encourage you to do that. But yeah, these limitations definitely exist. Yeah. How am I going? Yeah.
Sorry, I didn't super understand everything.
Sure.
So, I guess what I want a sense of is if I put effort into this, how's my life going to be better?
That's a good question. Yeah, so I'm soliciting a bit of trust in answering this question, okay? And that is to say, your life would be better in the same way that participants on the Lisp Reverse project's life would be better. So, does that appeal to you? Suppose I'm right. I would think that that's a better life. So you're not just writing the same thing over and over. I don't think anyone's interested in doing that. Certainly I'm not. I've never met someone who is. And if you are in fact not interested in doing that, then you would get benefits from learning these things. Because all this is we've all heard this don't repeat yourself stuff, right? Don't repeat yourself. And all this is just taken seriously. That's all it is. We actually really don't want to repeat ourselves. That's all it is. So if you think that's something that you aspire to, then I think you would benefit.
So what percent of those benefits available without doing the same style or hassle?
Yeah, good question. So so I've written a project, for example, called Functional Java, which is just functional programming in Java, and these limitations come up. And what do I do when I hit this wall? I copy and I paste. All right, and I think that the benefit here is simply I don't sit around pretending that there's some other way out of this. There's just not. And so I think like it's like a consolation prize, right? It's just, well, you know, I'm working in a type system. It says, you know, you're going to have a bad day, but try and make it good. Like, don't sit around trying to muck around and just copy and paste and get on with it. So I think the benefits you would get would be at least you're aware of the limitations and you can just make, you know, quick decisions. I think that's the best we can do. By the way, C# has monad comprehensions in it. Is there any C# people in here use C#? There's a lot of you. You've got link, right? We've all seen link. Do you know what link does? Link takes that join operation back there and turns it into syntax. That's all it is. Or select many. There's a relationship between select many and join. That relationship is equivalence, essentially. So you've already got it in there. It's in your language. You just can't abstract on the interface. I find that is awesome, right? There's people just like using monad comprehensions all around the place. And they say, what's a monad? It's the thing you just did. Cool. So I've got like 5 minutes left. I'd love to answer any questions you've got. Are there any more? Yeah?
I wonder if you have, just to bring it all home, a concrete example of implementation of monad you've used recently?
Well, yeah, just the maybe monad, which is like the potentially null one, is one that I've definitely used recently. I did a workshop yesterday where we had one where the monad represented the web framework stack. So all right, how about I go to sequence? Okay, so sequence, yeah, there. So imagine for a minute that I had a potentially null, so like I had a lot of potentially null values, and I didn't care which of them were null. All I cared about that all of them were not null. And this happens in everyday programming. All I do is I put them in a list and then just call sequence. And I'd inspect the result. And if I got that result back as null, then at least one of them was null. And if none of them were null, then I'd just have a list of values, all of which were not null. So, I mean, these kinds of things are like, they're just ubiquitous. They come up all the time. And so, does that help answer that question? Thanks. All right.
Sorry, I'm just sitting here going, should I write that in like a line of code?
Oh, the thing that I said, like, is it not? Yeah, sure.
So, like, I don't care, right?
You could, but the problem is so let's write that code, which is here, okay? And then you might come along to me and say, well, I could also write this bit of code. And what I'm trying to get at is these two bits of code are the same bits of code. They've repeated themselves. You may not recognize it straight away. You go, no, that's a different loop to that loop. Well, no, they share the same structure. They're just called sequence. So in this case here, there's no sort of potentially null going on, right? This is just applying to a function argument. And there's like a disparity, right? We go, well, no, there's potentially null over here and there's function application over here. They're two different things. And the point I'm trying to make is, no, actually they unify under a common pattern called sequence. And so I think I could really ram that point home if I came up to your code and you had these two loops sitting here and I'd come up to both of them and I'd just go, sequence. And it would just disappear. I think that would really make that point. Up the back there?
Yeah. So if these things are as powerful as you say they are, why aren't they at something like F#?
That's a good. Well, I've spoken to Don Syme actually. I felt like a real bully because Eric Meyer was standing next to me, and Eric's jumping around like, oh no, that's not how you do it, you know, as he does, and I think that simply the answer to the question is Don was unaware of the benefits of having done that. It's just that simple. So Eric's sitting here trying to convince other people that this does belong in your programming language, in his animated way. And And there was this argument happening in front of me, and I just happened to be on, Eric's team, and I felt like a bit of an arsehole, but, that's how it went. So I just think that's the best answer I can give. There's just unawareness, which is, you're all potential programming language designers, right? This belongs in your programming language. Let's not make this mistake again. I mean, you don't want to do it forever, right? I don't want to write sequence forever. I really don't. Sure.
I still didn't quite understand where C# and Java actually fall over at the moment. I mean, with generic and lambdas, etc.
Yep.
Why can't I express these?
Okay, so I'll get a little bit more detailed on that question. So let's just go to, say, Monad. So why can't you express these in C# or Java or F#? And that is, so see that T that we've got up there? How we've defined T over another type being A. And these things are called type constructors. That's just another fancy term. It's simply a value that you give a type to get a type. So we give like an integer to T to get a T of integer type. And the problem is you can't write these things in these type systems. You can't, this interface won't compile if you try to do it under C# or Java or anything. It just won't happen because the type system's not strong enough to do so. And there's a workaround to this, right? I've seen it. It's quite awesome, which is what people do is they'll go and use reflection and they'll look up and they'll go, is there a join method on the object? And if there is, then call it and get the value back. And if there's a join on that and so on. And they revert to turning off the type system. So yes, you can do it. It's just like a lot of gymnastics. You might as well just write sequence over and over. Yep.
So just to follow up on my other question, have you thought about putting up a Facebook site?
A Facebook site?
Yeah, I mean, that's basically what you want is a bunch of likes so that we get this in our language. I mean, I see the power, I see exactly what you're saying, but how do you win such a battle?
So I may know what a monad is, right? But when it comes to Facebook, I revert to my wife. Like, I'm not joking. I say to her, I've got this invite, I don't know what to do with it. Can you help me go? So maybe I can get your expertise on that, because I'm terrible at it. I don't know how to do it, other than to do what I'm doing here, which is just to encourage you all to ask questions and have the discussion. And if Facebook will help me do that, then awesome. This is my limitation now. So, all right, how are we going? So, a monad is just an interface. It has instances and it has derived operations. But the reason we do it is it's a damn useful interface. That's all. All right, thanks everyone.